Hello, everyone. Here is our lecture on periodic trends, the periodic table revisited. All right, let's get started. So, remember we talked about how the periodic table allows us to see trends or patterns from one atom or one element to the next. And so that's what we want to talk about today. And in fact, there are four patterns or four trends that we're going to discuss that you need to be familiar with. The first is atomic size. The second is ionization energy. The third is electronegativity. And the fourth is ionic size. Okay? And you should have read about all these in your reading that we assigned on Friday. So now we're going to see some pictures. We're going to talk through them in a lecture. Let's start with atomic size. So atomic size is basically the radius of your atom. How big is your atom? Think of it as a ball. What's the diameter of that ball? Okay, so as you move, so think about the periodic table. In fact, if you have one that you can sit next to you where you're taking notes and can kind of look at the periodic table as we walk through this, it would be helpful. Okay, so you'll remember that the columns in the periodic table are called groups, okay? And the rows are called periods. Keep that in mind too. So as you move down a group, in other words, as you're moving from row 1 to row 2 to row 3, the size of the atom increases. And that's because as you move from one row to the next, you have to add a new shell or orbital for electrons. You're adding more and more electrons around the nucleus and you need space to put them. So once one electron orbital is filled up, you have to add a new one that's even bigger around the outer one. And another thing that we want to think about is this idea of shielding. So you think of the nucleus as a sort of a ball of positive charges, and there is a cloud of electrons around that ball. The more electrons there are, and the more levels of electron orbitals that there are around the nucleus, the harder it is to kind of see the nucleus. In other words, it's shielded from the outside, if you will, by the cloud of electrons that surround it. And as you move from one row to the next down a group, the shielding of the nucleus gets bigger, gets more and more significant. There's more and more stuff between the nucleus and the outside world, if you will, and so it's shielded more and more. So that means that the atomic size, the size of the ball, increases as you move going down. And I have a graphic here that can help us look at that. So as we move down the rows in the periodic table, the starting with beryllium, which is of course in group 2, beryllium and magnesium group and calcium and strontium. This is going down, moving down the group 2 from row 2 to from row 2 to row 3 to row 4 to row 5. The size of the atom gets bigger and bigger, and I try to represent that with these increasingly large circles. So the atomic size, or sometimes this is referred to as the atomic radius, increases as you move down a column, as you're moving from one row to the next. Okay, that's the vertical component. What about the horizontal component? As you move across a period, so if you move from the left side of the table to the right side of the table, the atomic size decreases. Now that might seem confusing at first, but if you think about it, I think it makes sense. You don't have to be, as you move from, for example, beryllium to boron to carbon to oxygen from left to right across a row, you don't have to add new orbitals or shells for the electrons. You can just fill up the shell that you have. So the energy level is the same and the amount of shielding is the same, but you have increasing number of protons in that nucleus as you move from left to right. And those increasing number of protons represent a bigger and bigger pull on the negatively charged electrons. So that means that the electrons are pulled closer and closer to the nucleus as the nucleus gets more and more positive charges inside. So let's take a look at a graphic for that. That's what I have here. As we move across the columns from left to right, we have magnesium and aluminum and silicon and phosphorus, and you can see the size of the atom is decreasing as you move from left to right because there are more and more positive charges in the center of each atom that can pull more and more strongly on the electrons, pulling that electron cloud closer and closer as you move from here to here to here. All right? So atomic size will decrease as you move from left to right, and atomic size increases as you move from the top of the table to the bottom. Now here's a graph that's supposed to help represent that. It's a little fuzzy, and I don't know if it will help or not, but I'll throw it out there anyway. We're showing atomic radius measured in picometers on the y-axis, and we're measuring atomic number on the x-axis. Here is helium. That's at the end of period 1, the very first row. And as you move from helium, where'd my cursor go? As you move from helium to lithium, you're moving from row 1 to row 2. There's a big jump in atomic radius. And then as you move from helium to beryllium and so on across to neon, all in row 2, you can see that the size decreases. And then it takes another big jump as you go from the end of the second row to the beginning of the third row. All right, so you see the pattern here. The size decreases as you move left to right, but increases as you move from the top towards the bottom of the table. All right. Now, we talked a little bit about ions the other day, and ions represent an atom that has either lost or gained an electron, or maybe a couple of electrons. So when an atom loses or gains an electron, it becomes an ion. And of course, losing or gaining an electron is not free. There's a cost involved. So the amount of energy that is required to remove an electron from an atom is called the ionization energy. This is how much it costs to strip away an electron from that atom. All right, so to the trend. As you move down from the top of the table towards the bottom of the table, the ionization energy decreases. The cost gets lower and lower to strip away or to steal an electron as you move from the top of the table towards the bottom. And as you move across a period, as you move from the left side of the table to the right, the ionization energy increases. It gets harder and harder to pull or strip away or steal an electron from an atom as you move from the left side of the table to the right side of the table. All right, so let's see a graphic for that. So here we have some atoms, beryllium, boron, carbon, nitrogen, oxygen. We're moving across this period, and you'll remember, as you move across a period, the atomic size decreases, right? All right, so, and as we move from the left to the right, the ionization energy increases. Now, the reason this happens is because those electrons that are surrounding these, that are in clouds surrounding each nucleus, they're the same distance from the nucleus as you move across. There's not a new electron orbit, right, like you get when you move down the table. As you move across, you're filling up the same orbit. So the electrons are the same distance from the nucleus as you move from here to here to here. However, there's more positive charge in the nucleus as you move from here to here. So, carbon has 6 protons, nitrogen has 7 protons, oxygen has 8 protons. These protons are pulling, this larger number of protons can pull more and more strongly on the electrons, which makes the radius smaller, like we said a couple minutes ago, and it also makes it more and more expensive to steal an electron from one of these atoms. So it's relatively cheap for beryllium to lose an electron. It's relatively expensive for oxygen to do so. So the ionization energy, or the cost in energy, increases as you move across the table. Similarly, like we said a minute ago, the the atomic size increases as you move down because you have to add whole new electron shells as you move from row 2 to row 3 to row 4 and so on. All right, so beryllium to magnesium to calcium to strontium, the atom's radius is getting bigger. That means that each successive shell of electrons or orbit of electrons is further and further away from the nucleus. All right, further away from the nucleus, and that means it's not as tightly held. It's not the protons in the nucleus can't hold on as tightly to an electron that's really far away as it can to an electron that's really close. So the energy cost to steal an electron from strontium is much less than the energy cost to steal away an electron from beryllium, because the strontium's valence electrons are so far away from the nucleus, they're easy to steal. All right. The third trend that we want to talk about is called electronegativity, and this is the tendency of an atom to attract electrons, or as I like to think of it, is how big of an electron hog is the atom. Some atoms really, really like to be electron hogs. Some much less so. And the way this trend works is based on the element fluorine. Fluorine is the most electronegative element on the periodic table. And as you move away from fluorine in any direction to the right or down, the electronegativity decreases. The atom is less and less of an electron hog as you move away from fluorine. Here's a graphic that shows us that. So fluorine is right here in the upper right corner. Any direction you move, this direction or move down the table or even move diagonally away from fluorine, any way you move away from fluorine, your electronegativity will decrease. Or the way this graphic shows it, electronegativity increases as you move closer and closer to fluorine. All right, so that's just this electronegativity trend is actually a pretty straightforward one. Find fluorine, and then the further away you are from fluorine, the less electronegative is that atom. The last trend that we want to take a look at is ionic size. So remember we talked about atomic size and how it changes a few slides ago. Now we want to talk about ionic size. What happens to the radius of an atom when it becomes an ion? Okay, so as we move down a group, so from row 1 to row 2 to row 3, the size of the ion increases, just like the size of the atom increases. And if you think about it, that should make sense because there are more orbitals, there are more electron shells around the atom as you move from row 1 to row 2 to row 3, so the size is larger. The wrinkle comes in when we move across a period. So as you move across a period, the size of the ion decreases for cations, which are positive ions, and increases for anions, which is negative ion. All right. So if you think about it, at first that might sound confusing, but I think it makes sense. A cation is positively charged, which means it's missing an electron. So or maybe more than one electron. To make a cation, you have to take away something from the atom. When you take something away from the atom, the radius gets smaller. Similarly, an anion is negative, which means you've added one or more electrons to it. If you're adding something to the atom, it makes sense that the size of the atom should get bigger. Let's see that in a graphic. All right, so here is lithium and sodium and potassium, and you can see the ionic size, the size of the atom, the atomic size increases as you go down, lithium to sodium to potassium. But if you compare the lithium atom to the lithium ion, which has lost an electron, the radius is smaller. There's a smaller dot. The blue ball is smaller than the yellow ball because lithium Li plus is missing an electron. It's missing something, so it's smaller. And what's actually happening is there's a collection of positive charges in the nucleus, these protons in the nucleus, and they pull on the electrons. Well, when you make an ion, by taking away one electron, now the protons outnumber the electrons. There are 3 protons, but only 2 electrons in lithium plus, Li plus, which means that those protons can pull even harder on the remaining electrons and pull them closer, which means the radius decreases. And that's what we see in these trends. Sodium atom compared to sodium ion, the ion is smaller because there are fewer electrons, and that means that the positive-negative balance is upset. The protons can pull even harder on those remaining electrons and pull them close. And we see these trends in the second and third groups as well. Now, when we get to the other side, to the right side of the periodic table, and we're not making positively charged cations anymore, we're instead making negatively charged anions. In this case, to go from nitrogen, for example, to its ion, N-3, you have to add 3 electrons to go from here to here. All right? And you're adding something to it. It makes sense that the atom needs to be bigger. So the radius increases as you add electrons to go from nitrogen atom to nitrogen ion. Same for oxygen atom to oxygen ion, fluorine atom to fluorine ion. All right, you see the trend? So for anions, when you make an anion, the radius is increasing. When you make a cation, the radius is decreasing. All right, and that's kind of shown in these next 2 slides. They may or may not be useful to you, depending on how visually oriented you are. Here again is the radius on the y-axis and atomic number on the x-axis. Here's this approximate atomic size for lithium at about 150 picometers, and the lithium ion, Li+, is on something around 60 picometers, so much smaller radius when you went from the lithium atom to the lithium ion. Okay. Opposite is true when you're making anions. So where's my cursor? Here's fluorine, and here's the fluorine ion, fluorine atom, a fluorine ion. So as you move from the atom to the ion, by adding an electron, your radius increases in size. All right. The last slide here is a summary slide, and it shows the trends across the periodic table for ionization energy here in red, for electronegativity in light blue, and for atomic radius in purple. I don't try to show the trends in ionic size that we just got done talking about because they're more complicated. So I would refer you to the previous two slides to review the trends for those. That's it for today. Thank you.